Time to talk about the Anti-Markovnikov addition of HBr onto alkenes. By definition, the Anti-Markovnikov addition is a reaction in which the least electronegative element, in this case H, attaches to the carbon that has the least amount of H's. So this carbon has 0 H's, that carbon has 1 H. So the H attaches to the carbon here on the left side and the bromine attaches to the carbon on the right side. This is an anti-Markovnikov product, simply because it's doing the opposite of what Markovnikov stated that tends to happen during an addition reaction. The various thing about this is that while some laboratories reported this type of reaction, the fact that now we're seeing some anti-Markovnikov additions, there were many other laboratories that were seeing the opposite effect. They were using HBr and they were getting results like Markovnikov did, or what Markovnikov would predict. But then there were these other labs that would do the same experiment with the same reagents, or so they thought, and they would get the anti-Markovnikov result. So something was definitely different, and it wasn't specifically obvious as to what that may have been. But what ultimately ended up happening was that it was found that many of the groups that were having these anti-Markovnikov results upon their addition reactions were using solvents that were old, specifically old etherates. And this seemed to be the source of the problem. Now you might wonder, was like, well, okay, they're using old solvents, so what? Like, what's the big deal? Well, the thing is this. When you have solvents, especially solvents that are exposed to the atmosphere, oxygen dissolves in the solvent. And depending on what type of bond you have, you may be able to break some of them. So in your typical hydrocarbons, your typical ethers, you could have carbon-hydrogen bonds that lie below the 435 kilojoule per mole bond dissociation enthalpy. And dioxygen in particular can engage itself in radical reactions, because you may recall from general chemistry, dioxygen is actually a diradical. We know that from the molecular orbital description of dioxygen as a molecule. And so having dioxygen sitting in your solvent for long enough, if your bonds are just low enough in energy, you can end up producing some radicals. So in the case of ethers, this is actually kind of problematic, because this carbon-hydrogen bond is actually lowering energy than your typical carbon-hydrogen bond as a result of the inductive effect produced by the oxygen of the ether. Right? So the oxygen is withdrawing electron density, making this bond less likely to stick its electrons evenly between that carbon and that hydrogen. And so dioxygen, that's technically diradical, depicted as such in this drawing, over time will react with your molecules via a radical process. It will abstract a hydrogen atom. It will produce the monoradical hydrogen peroxide, and you will also have an organic radical. Now these two can actually come in place, meet together, and terminate, producing an organic radical. Now what you can see here is the calculation of how much energy that takes. The breaking of that carbon-hydrogen bond, if we go with the worst possible outcome, which would be the typical carbon-hydrogen bond dissociation enthalpy of 435, and subtract the energy that it takes to form the oxygen-hydrogen bond in a peroxide, that costs about 50 kilojoules per mole. But then when you have this termination event happening to form your organic peroxide, you get back more than enough energy to make up for the energy you're using up in the first process. So given enough time, your etherate solvent is going to end up forming these radicals. And of course, exposure to light or even some mild heating will ensure that this oxygen-oxygen bond is broken, producing more radicals. This can be a major problem, because if you do have solvents that have been left open, well, even if they haven't been left open, but if they have been open in the atmosphere and just put aside and forgot them for like a long time, what happens is that you form these organic peroxides that are very prone to exploding. And this is the big problem with them. So the idea is that if you have to work in a chemistry lab, it's best that you keep track of your ether rates and you're always checking to make sure that there is no major buildup of the radicals. And there is inorganic materials that can tell you this just by color differences easily, whether you have radicals or not. And you can always quench them by using the proper reagent. Typically, iron 2 sulfate will be good enough to quench the radicals. But if you have an iterate bottle for which you've basically neglected the bottle and it's been sitting there for like a year or longer, there's a chance you're going to form these organic peroxide salts that are highly explosive. And in those cases, you actually want to call the bomb squad to like take them out, because even a bottle like this can blow up an entire lab. So it's it's best not to mess with them. So looking back at the oxygen, specifically the oxygen-oxygen bond of a peroxide, is worth reminding you that that bond is only worth 214 kilojoules per mole, and that's low enough in energy that even visible light is enough to break the bond homolytically and produce the radicals. So yeah, if you have this bottle present, and it has been exposed to dioxygen, you're probably going to produce some radicals over the course of its lifetime. And now this kind of brings us to the point with the HBr, because um, some labs were seeing that you were having this anti-Markovnikov addition, right? But let's see what's happening, right? Because if we're forming radicals in the iterate solvents, well, HBr can actually react with that radical, right? So if you have your peroxide radical forming right here, that can react with HBr. It abstracts a hydrogen atom, producing your organic peroxide or your hydrogen peroxide. It also produces a bromine radical, which can continue the process of radical mechanisms. But if you look at the energy of creating that peroxide OH bond and breaking the HBr bond, this is slightly exothermic. So this is actually a favorable reaction. Compare that to HCl, which is a reagent for which this business of seeing the anti-Markovnikov reaction was never really observed. Here you can understand why it was never observed, because when you look at the formation of the organic OH bond, the abstraction of hydrogen, and you compare it to how much energy you have to put in to break the HCl bond, well, the overall energy difference is positive, meaning that you actually have to put in energy for this process to happen. So you never actually produce chlorine radicals, in your iterate solvents. But if you use HBr, that's where it is likely that a radical bromine can actually be formed. All right, so this is really the key idea. For anti-Markovnikov additions, we are going to be dealing with HBr and radicals. So you have radicals, you have HBr, you're dealing with an anti-Markovnikov addition. Now, to explain why the formation of a radical ultimately leads to the anti-Markovnikov addition, we once again need to analyze the process in a mechanistic way, step by step, to see what intermediates we're producing. And an alkene can still react with a radical the same way that it can react with an electrophile or a carbocation, um, but this time it's going to do it via one electron, right? So you'll have one electron of the pi bond interacting with the electron of the radical bromine to form a new carbon-bromine bond. But at the same time, you're going to produce a new organic radical, right? So if you make the bond such that it ends up on the right carbon of the alkene, the radical will end up on the left carbon of the alkene. All right, and that's a tertiary radical. So that looks actually pretty good, right? Because tertiary radicals are more stable than secondary radicals, which themselves are more stable than primary radicals. So if bromine attaches to the carbon that has the most H's, because it's a radical, it will lead to formation of the better, more stable radical, in this case a tertiary radical. If you were to attach to the carbon with the least amount of H's, you will produce a secondary radical which is not as stable. So then the argument is exactly the same one as that of the carbocations. You're trying to form the better carbocation. And it turns out that when you're dealing with radicals, the radical that starts the process is that of the more electronegative element. So the first attachment, is now via the opposite element of the electrophile. And this is the reason why you end up with this kind of like opposite effect. Because once that organic radical is formed, now that can react with an equivalent of HBr. And keep in mind that when these radical reactions are happening, the radical is always present in a minute amount, right? So you have most of the HBr is still present as HBr, but some amount of it has turned into Br radical. And the thing about Br radicals is that by the time that this organic radical reacts with HBr to abstract that proton and complete the process, you have reformed Br radical. So it doesn't take much of the radical to be present to continue the process, because it's actually a catalytic process that keeps going and going and going. So this is ultimately what happened with those laboratories in Europe that had this outcome with anti-Markovnikov additions. They were dealing with radicals. And much like the mechanism for explaining which carbocation is going to be the preferred one leading up to the preferred and most stable product of addition, this is another mechanism that you have to be aware of and you need to know. All right, so that basically explains the whole business. HBr is prone to forming radicals because of the bond dissociation enthalpy differences, and if you use it in the presence of old etherate solvents, you're probably going to form bromine radicals that will lead to the anti-Markovnikov addition of alkenes. All right, so that completes the explanation of anti-Markovnikov additions. In the next video, we're going to talk yet about another type of addition reaction, one that creates some interesting type of rings involving the original alkene. So I'll see you in the next video.